Hello, in this video we are going to be looking at derivatives of logarithmic functions. We're going to begin just with a little bit of a reminder about what a logarithmic function is, and then we'll get into taking their derivatives. So y equals log base a of x is a relationship between x and y that is synonymous with the relationship a to the y is equal to x. So let's unpack this a little bit. When we say that y is a logarithm, what we mean is that y is the exponent, and then the rest of the logarithm describes what type of exponent y is. Y is an exponent that a needs to be equal to x, and that's what this expression here says. Y is the exponent that a needs to be equal to x. There's certain applications where having logarithms is very useful, so it's just worth taking a little bit of time to talk about them. Something we will see very commonly is the natural logarithm, and that is when your logarithm has a base of e. So a couple of just generic things we can say about logarithms. Logarithms always have a domain greater than 0. You're not allowed to put 0 into a logarithm. The function would have been undefined over here. So we have this vertical asymptote at x equals 0, and then this function is increasing. Initially it increases very rapidly, and then you hit 1, and the slope right here is just 1, and then as you continue on, the slope becomes less and less and less. So what is being shown here in this graph is indicative of what the derivative rule is going to be, and you can see this derivative rule down here at the bottom of the page. But before you look there, if you knew this information was true, you might have a good guess as to what the rule would be. Remember that the derivative of a function tells you the slope of the function at that point. So what we see here is that if the x value is 1/4, then the derivative, the slope of the tangent line, ends up giving us 4. So like, what's the relationship between 1/4 and 4? Then we see that if we pick an x value of 1, our slope is 1. You can ask yourself, what's that relationship? And then if we pick a point of 3, the slope of the tangent line becomes 1/3. Ask yourself, what's that relationship? And then you'll see the same pattern going on. And what we see every time is that the slope, or the derivative, ends up being the reciprocal of the initial value that we picked, the x value that we picked. So let's go down and state formally what is the definition of a natural logarithm. For a natural logarithm, the derivative of that function is always just going to be 1 over x, so it's basically the reciprocal of whatever that x value was. Now, there is a very straightforward application, which is like, let's say if f of x is equal to the natural log of x, then f prime is equal to 1 over x. Hooray! I mean, that's what this says. But there's other applications that start to like add more stuff in. Well, what if g of x is equal to like 5 times the natural log of x? Well, we know how to handle constants when we take derivatives. This would just mean that g prime is equal to 5 times whatever the derivative is. And then we ask ourselves, what is the derivative of the natural log of x? Well, it's just 1 over x. So then 5 times 1 over x is 5 over x. So those are the initial just applications of being able to take the derivative of a natural log function. Something I've shown before in class, that it's just an interesting relationship. It doesn't really have any bearing on what we're doing, but I like to point it out, is that we have this little chain of derivatives. If you take a 4th degree polynomial, so like x to the 4th, and find its derivative, you're going to get 4x cubed. Now, I'm not going to keep track of what the coefficients are. I'm just going to keep track of the degree of the polynomial. So what we saw was we saw the degree of the polynomial reduces. If you take that derivative, it gives you x squared. If you take that derivative, it gives you x to the 1st. If you take the derivative of x to the 1st, you get x to the 0. And then the chain kind of breaks, because if you take the derivative of 0, it just goes back to 0. We know that if you could ever somehow get to x to the negative 1 and take its derivative, then what we end up with is -1 times x to the -2. If you ever took the derivative of x to the -2, we get -2 times x to the -3. So we see this chain kind of propagating itself off towards infinity. But what function could give you a derivative of x to the -1? Well, the answer is that the natural logarithm would be the start of this chain. So the natural log of x, if you take its derivative, it gives you x to the -1, and that would start off this type of a chain. And it's fun to point out that that relationship kind of exists. Okay, let's think about another application of this derivative, and this is really the one you are going to use most frequently. What it says is that if you have an expression inside of your natural logarithm, we can still take the derivative, we're just going to have to apply the chain rule. So this may not look like the chain rule to you, but it is the chain rule. If you want to take the derivative with respect to x, you start by saying, okay, it's 1 over whatever nonsense you had before, and then afterwards you have to take the derivative of that nonsense with respect to x. So you may be used to seeing the chain rule written out as the derivative with respect to x of f of g of x is equal to, it's f prime of g of x, and then g prime of x at the very end. And this is the same relationship. Basically, u is equal to g, so then du dx is equal to g prime of x. Now, this all may look like just a bunch of like mathematical lingo that doesn't really make you feel very confident about applying this. So if this looks too confusing, just ignore it for now, and let's look at a couple of examples that hopefully clarify what we're talking about. Could you find the derivative of f if f was, let's say, the natural log of 4x? Well, the way you would do this is you would say f prime is equal to 1 over, now keep in mind, this 4x, if we were phrasing it in terms of the expression or the rule that we just saw, 4x is like taking the place of u, so u is equal to 4x. But the idea is that it is the inside function. So when we start, we take the derivative of the outside function. So the derivative of a natural logarithm is always 1 over something. So what is that something? It's just 4x in this example. And then, hooray, we took the derivative, but now you must chain on something. What do you chain on? You chain on the derivative of the inside. Okay, so then we are going to multiply by the derivative of the inside, which is just 4. And this is something that can be simplified. So it turns out that we end up with 4 over 4x, which is just equal to 1 over x. Now, you look at this and you're like, oh my goodness, I think I see a pattern. Maybe the natural log of anything will just always simplify to 1 over x. I wish that was true, but it is not. So let's look at another example where this doesn't hold. What if g was equal to the natural log of x squared plus 3x minus 7? Well then, g prime would be 1 over all of that. And at its core, like, this is, the derivative of a natural log is very easy to remember. It's just 1 over whatever was inside. But you can never stop there. You always have to chain on the derivative of the inside part. So now we'll multiply by 2x plus 3, and then we'll see, like, okay, yeah, in the previous example, the 4 and the 4 reduced and you just had 1 over x, but there's no way that 2x plus 3 is going to reduce with this denominator somehow and magically give us 1 over x. It's just not going to happen. So what do? We don't do anything. We just simplify it as 2x plus 3 over x squared plus 3x minus 7, like so. All right, the next thing we want to talk about is that there are properties of logarithms that come out of algebra. Now, don't look at this and feel like, I'm going to have to remember all of this. You don't, but there are certain properties that end up being very useful. Let me highlight what those are. those are these three over on the left. So 1, 2, 3. And the corresponding implication, so this is for a base A logarithm, the corresponding implication is that these three things over here would also be true. So let's talk briefly about what they are. If you're ever multiplying inside a logarithm, you can split this up as addition of two separate logarithms. If you divide, division turns into subtraction of the two different logarithms. And if you ever have an exponent inside your logarithm, you can pull it out as a coefficient in front of the new logarithm. So let's go ahead and see an example where that would be the case. What if y is equal to the natural log of x over x minus 2? Well, we could, so I guess what is the question? Let's compute y prime. Now, there's a couple things we can do to compute y prime. So one of them is we could try to think about just starting out with this is going to be 1 over the expression that's inside. I'm not actually going to do this, so I'm going to write it in blue, then I'll go back and erase it. So 1 over x minus 2. Okay, then you would have to chain on the derivative, so dx of whatever x over x minus 2 is. Now, this is kind of hard to think about. We have ways to think about this. We have a quotient rule. We never really talked about it in this class a lot, but there's a quotient rule that will let you take this derivative. You could take the denominator, give it an exponent of -1, and so then you could apply like a product rule and a chain rule at the same time, and you look at this and you're like, wow, that seems like a huge headache. It is a huge headache regardless of how you do it, but it doesn't have to be. So this property, let's see which one it is. Which one is it? The property 4 up here gives us a really easy way to compute the derivative without any of this nonsense. So let me grab my eraser, erase all of this blue stuff, and let's go back and think about, okay, well, how do we actually want to do this problem? What we do is we say, I know that if I'm dividing two things in a logarithm, I can rewrite this as two separate logarithms. Sorry, that should be ln. And what's the relationship between those two logarithms? If I was dividing in the argument of the logarithm, I'm going to be subtracting the two separate logarithms. So division turns into subtraction, like so. Now let's find this derivative. So this derivative was hard to think about. This derivative is super easy to think about. What is the derivative of 1 over, sorry, I said it. What is the derivative of x? It's 1 over, my words. What's the derivative of the natural log of x? It's 1 over x. What is the derivative of this? Well, let's be a little bit careful. We're going to be subtracting. It's going to be 1 over, you start by just saying it's 1 over the inside, but then like, aha, I need to chain something on. What is the derivative of that denominator? Well, the derivative of x would just be 1. So yes, you have to think about chaining, but you just multiplied by 1, so really I don't need to write that in there. Let me get rid of it. This is my answer. That's all there is. Now, you may see people simplify this by actually subtracting these two things together. That's like an algebra simplification that you can choose to do if you would like to. I'll show it to you over here in red. I guess maybe blue to indicate that you don't need to do this, but if you want to, you can. So this is x minus 2 over x times x minus 2 minus x over x times x minus 2. What I did here, if you care, is I just multiplied these two denominators together. If you multiply x minus 2 to the left fraction, you also have to multiply it to its numerator, so we see that we get x minus 2 over x minus 2 in a way that would simplify to just be 1 over x like we used to have. When you multiply x to the right fraction, that has to go to the numerator and the denominator. So now when you're looking at this, you could actually subtract their numerators. X minus x is 0, so final answer is going to end up being -2 over x times x minus 2, like so. But again, for the purposes of this class, the first expression is going to be completely fine for me. Let's look at one more way that we can use some of these properties to just make our lives a little bit easier. Let's suppose that you have h of x is equal to the natural log of, and I'll do parentheses x to the 4 plus 7, close parentheses, raised up to the third, close parentheses again. So this is an expression that you can just take the derivative of. If you're trying to find h prime of x, I'm going to put this in blue because I'm going to go back and erase it in just a minute. This would be 1 over whatever you used to have, so that's x to the 4 plus 7, and that's being cubed. But then you would have to chain on the, so this is a chain, you would chain on the derivative of that, which would be 3 times what's in parentheses raised up to the 2, so just this stuff would go right here, x to the 4 plus 7. But then that's another chain rule, so then we chain again, and then it would be 4x cubed. And then you would simplify all of this. So looking at this, I'm trying to make it look obnoxious. It's really not. It's like very manageable, but there's a much cleaner way to do it than what I was describing. So let's take the clean approach. As long as we remember property 5. Property 5 says if you're ever taking a natural log of something raised up to an exponent, you can just immediately take the exponent and bring it outside as a coefficient. So this 3 is allowed to migrate out to the front as a coefficient. So this is 3 natural log of x to the 4 plus 7. Now, why is that helpful for us? Because if it's a coefficient, I don't have to do anything special when I take its derivative. It just stays out in front. Then it's going to be 1 over x to the 4 plus 7. And then, yes, we have to now chain on the derivative of x to the 4 plus 7. But that's very easy to think about because there was just one chain happening. So what's the derivative of that? It would be 4x cubed. Okay? This is our answer. You want to simplify it. So we look at this like 3 times 4 is 12 times x cubed. None of these are in a denominator, so I'm going to put them all up here in the numerator. So this is going to become 12x cubed over x to the 4 plus 7. All right, the final thing we want to do to round out our notes for this section is talk about derivatives of other types of logarithms. So we know the derivative of the natural logarithm is 1 over x. What about the derivative of a log base 2 of x? Actually, let's ask that. What if y is equal to log base 2 of x? Then y prime would be, well, what we're going to do is, first of all, we are going to rewrite the logarithm using the change of base formula. So the change of base formula simply says that you can rewrite one if you have a logarithm base you don't like, you can rewrite it using a logarithm base you do like. We're going to pick the natural log of x. And the way that you do this is that the previous argument goes up in the numerator, so it's going to be the natural log of the previous argument divided by the base that you didn't like is going to go in your denominator, and it'll be the natural log of that number. Okay, so if we apply that to this example, like how do we rewrite this? This is going to be the natural log of x over the natural log of 2. I have not yet taken a derivative, but now that I'm seeing this, remember that like x is the variable, natural log of 2, this is a constant. If you put it in your calculator, natural log of 2 is just some non-ending decimal, but it's a constant. So what do we have? We really have 1 over the natural log of 2 times natural log of x, if you want to think about it that way. Okay, now, my initial question was I have y, and I want to compute y prime. Now that I've rewritten y in this manner, y prime should be very straightforward. This is going to be 1 over the natural log of 2 times 1 over x. That's our answer. Now, if you want, you can show this all in the same line. 1 over x natural log 2 would be the common way that you would write that, but this line here was correct. Well, what if it's a little bit more involved than that? What if you had g of x equals log base 6 of x to the 4 minus 2x cubed plus 3? Well, you start by rewriting g. This is natural log of x to the 4 minus 2x cubed plus 3 over the natural log of the thing you didn't like, which was 6. So then g prime is going to be 1 over the natural log of 6 times, okay, and then I'm going to take the derivative of that numerator, so that's 1 over x to the 4 minus 2x cubed plus 3. And if this was class, I would ask everyone, hey, are we done here? Do we need to add anything else? Does anyone want to put a chain rule over here? And you guys would all stare at me and be like, why is he asking me this? Okay, I'm joking. So then 4x cubed minus 6x squared. This is our answer. Let's go ahead and simplify it a tiny bit. So what we have is just 4x cubed minus 6x squared over natural log of 6 times x to the 4 minus 2x cubed plus 3. All right, that finishes the notes for this section. So what we have at its core is we have a new derivative. We now know how to compute the derivative of the natural log of x. And so if this was f, then f prime becomes 1 over x. And then we can apply it using the chain rule, which we saw several times.